Hi, everyone. We are here starting off chapter 12. Section 12.1 is about vector valued functions. And if you look closely, zoom in, enhance. Whoa, man, why does that always do that? That makes it so much less dramatic. Okay, we are actually going to do differentiation and integration today. We're going to do some calculus in a multivariable calculus class. So yeah, get excited for that. Actually, we're going to throw limits in there too, because I don't know, we're feeling ambitious. No, it's part of the curriculum. So we are still in 3 dimensions, but the idea here is that we are working with parametric equations that are vectors. In the past, you may recall in chapter 9, doing some calculus on parametric equations already. You know, for instance, this fish shape is, given by some parametric equations where you've got x is equal to t squared and y is equal to t cubed minus 3t. But the idea is, as you transition from values from -2 to +2 in terms of t, you trace your way around this fish. So starting here, we go past -1, 0, 1, and finish the fish. And that's what we're going to be doing, but now in space. And the thing that's going to be tracing these curves in space, what's going to be tracing them out is a vector that's going to change along with our parameter. So we're normally going to use r of t as kind of our default name for a space curve, just like we use f of x for a function. And all 3 components of this vector are going to be little functions of t, f, g, and h. Sure. Know that this vector notation is equivalent to writing out separate parametric equations: x equals some function of t, y equals some function of t, and z equals some function of t. So that's what we're doing. We're talking about space curves today. And here's our first one. We've got r of t is equal to cosine of t, comma sine t, comma t. And t is going to range from -2 pi to 2 pi. And yes, this describes a helix. Let's go ahead and take a look at that. And again, we're going to do the cross sections thing where we look at this function in different ways to kind of see how the cosine, sine, and t come into play. But yeah, let's go ahead and do this. A little GeoGebra. All right, so here's our helix. And one of the things, I might as well show you this live. I'm just gonna re-go over this, but in order to get a space curve, I guess there's a couple different ways to do it, but one of the most robust ways is to type in curve. And then, well, actually, let me leave this up. What we're going to aim for is an expression in terms of t, but this is for the x component, then the y component, then the z component. Then we have to tell it that we're using t as a parameter, and we get some start and end values for t. So the idea here would be cosine of t, comma, sine of t for the y value, comma, t for the z value, then t again, because we're telling it we're using the parameter t, and then whatever, I'm just going to go from -7 to 7. I forget what the exact things were. That'll give us a curve that's actually a little bit more. Ooh, okay, and that gives us the black space curve. I'm going to bring this one back because I actually did that one Oh, from negative 2 pi to 2 pi. That makes sense. But yeah, here we go. One of the things that I've done to show you how this thing gets traced out as t changes is I've made a slider, call it W. Slider is able to go from negative 5 to 5, but since I've defined the curve to be A, if I take A of W, that plugs this value in for t in the original equation so that we get a point that travels along that curve. And normally for this kind of thing, I'm going to use a point so that it just travels along the curve. But know that this is a vector valued function, and it's written as a vector. So simultaneously, I mean, you can think of this as a vector coming from the origin, and just the tip of that vector is tracing out the space curve. So now there's a little orange vector, and if you want to think about the vector valued function that way, that's cool. But normally, I like to leave the actual vector looking things for like a tangent vector along this curve that we'll see soon. Actually, here, that's the position vector. Did I? No, that's the other thing. Did I make a tangent vector on this one? Nope. Nope. Okay. We will see a tangent vector soon. But before I forget, I wanted to look at the different cross sections of this helix because we get to look at it. It's really cool and spinny. But if we want to analyze this and break it down, one of the things that we could do is look at it perpendicular to a bunch of different axes. And here, this is what happens if you look down, straight down the z-axis onto the xy plane. We have a circle. And that makes sense because when you parameterize a curve with cosine and sine, you're just going to travel around the unit circle, starting, at 0. Oh, that's the positive x direction. I bet I should, there we go. We can switch it. That looks like an xy plane. And then, okay, it's going backwards, but yeah, you would see this just travel around the circle as the value of t changes. So we have a circle kind of cross section or shadow when we look down on the xy plane. And very similarly, when we look from the side, I guess now we're looking down the x axis, if I can get this right. Boom. And so we're looking in the YZ plane. This thing looks like a sine function. And indeed, yeah. There's the sine shadow that matches up nicely. We've also got a cosine function if we rotate it around and look down the y-axis. So we get the cosine function because cosine's our x value and t is our z value. So yeah, as this changes, it traces out a cosine function this way. So that's just a neat way that you can kind of look at a couple components at each time and look at the relationships between two components. But yeah, all in all, you get this cool thing. And this is one of the major reasons I love this course. We're going to get some really cool pictures to look at. All right. So that was really just to introduce you to what that looks like. And know that the parameterization here, where x equals cosine of t and y equals sine of t, using basically polar coordinates, that's really handy because it allows us to travel around a whole circle. If you were to use a different kind of parameterization, that could be possible, but know that we're going to want to put functions of t inside of these parameters. And so a lot of times, like for instance, if I was going to make x equal to t, then in order to travel around a circle shape, I would need to make y like the square root of 1 minus t squared. And you'd only get like the top half of the circle because that's the only way that you could do that with a function. And you'd have to maybe do like a piecewise defined kind of thing. I don't know. Yeah, you'd have to combine two vector valued functions in order to actually get the entire circle covered in. So the parameterization can be kind of something that's elegant if you find the right kind of thing, but a parameterization is not unique. We could come up with the same curve a different way. Okay, so I just used that GeoGebra link. Okay, first things first, limits of vector functions. Then we'll do derivatives and integrals. Here's a limit. I bet you weren't expecting to see epsilons and deltas today. So back in Calculus 1, there's a section, maybe section 2.4 in our calculus textbook that laid out a limit definition of the derivative using epsilons and deltas. And the idea is we have an epsilon bound in the y direction, and we had a delta bound in the x direction. And the idea is we can say that a limit exists when we can get arbitrarily close to L, our limiting y value there, as long as we get sufficiently close to C, our x value that we're evaluating the limit at. And so we'd like to be able to shrink epsilon down and down and down and down and down. But right now, if we used this wide of a delta band, we would not be guaranteed to land in this set of y values if we put in this set of x values. We could land outside it. We could land here, 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 here. All of those are lower than the band where we want to be in. All of these are above the band that we want to be in. So we're too far away from L. But if we shrink delta maybe down to this small, then now we've chosen to be close enough to our value C in the x direction such that we are completely close to the L in the y value, so that any x value that we input here will land safely within the epsilon range. The problem is that we want, epsilon to be arbitrarily close. So we want to be able to shrink that smaller and smaller and smaller. And now our delta band, and there's this whole chase thing that goes on. The idea of a limit actually existing is you want to be able to define delta in terms of epsilon. And I think choosing epsilon over 2 is a good choice in this one. So real quick, I'm going to do this. Yes, okay. And the idea here is now that once you've identified and defined delta as a function of epsilon, what you're able to do is change epsilon and delta changes along with it so that you get this perfect matchup between the two. And then you can be confident that no matter how small you make epsilon, you're always going to have a delta that works right along with it. In our context, in the vector functions context, we're working in 3-dimensional space. And so now the boundaries don't look exactly like they did before. Here, for the delta boundary, we are just trying to find values that are sufficiently close to t. This inequality says that. We're trying to find, or well, we were trying to find t values that are sufficiently close to a. A is the thing that we are approaching in this limit, and we're hoping to get L as our limiting value out of it. But notice that L in this case is no longer just a y value, it's actually a vector. So what we're trying to do, and yeah, you can think of it as a vector or you can think of it as a point. I tend to think of L as being a point in space, and what we're trying to do is get arbitrarily close to L along some space curve, a path that hopefully goes through L. And this inequality over here describes the difference between two vectors, and this is now the magnitude of a vector. So the magnitude of a vector is very much like distance. So when we are trying to minimize this distance, it basically means that we're trying to get closer and closer to the point from any point in space where L is the center of basically a sphere. We would call it an epsilon ball. So if I click on this, this is what the picture looks like. And I know it's kind of wild. But L, our limiting value, is a point in 3D space, or you can think of it as a vector. But let me stop this because that's distracting. Epsilon now gives us a ball around that point. And again, we would like to be able to shrink that ball as much as we possibly can. But so I don't know, if we shrink epsilon down to 2, we have a sphere of radius 2 around the point L. If we want to shrink delta enough so that we fit inside of that ball, here I'm shrinking delta, and delta is that green band that I have along here. The idea is that we want to shrink that green band so that all of the green band is contained inside of epsilon, and no matter which value of t we put in, as long as it's sufficiently close to the t value corresponding to L, which I guess in this case is pi. I don't know why I did that. So yeah, I guess, no, that's fine. But yeah, our L point is -1, 0, and then pi. Yeah, this is our kind of cycling through everything in our delta interval and showing that the function is always close enough to L to be within our sphere. And again, you do the whole chasing thing with shrinking epsilon, and oh no, now the green part is outside of the ball, so we've got to shrink delta too. And the idea would be, can you come up with some function of epsilon? Yeah, can you describe delta as some function of epsilon to make those two things coordinate? I'm not going to do that right now, but I was hoping that just looking at that would give you an idea of what a limit looks like in terms of these vector functions. We're going to do more limits when we start doing multivariable calculus, and in the way that we would put multiple variables like x and y into a function. Right now, it's a vector valued function because we're putting in one parameter and there are 3 component outputs. But yeah, limit just boils down to shrinking the distance between the components and the limiting point So this is, yeah, just Euclidean distance here. And in order to get this whole square root thing to approach 0, all of the individual components need to approach 0 as well. So what a limit looks like in this context is actually just doing 3 little limits, one for each of the components for x, y, and z. And so we have an example here where we've got 3 little functions of t for the x, y, and z component, and solving for those limits is just as simple as evaluating those individually. And if you were ever to get one of these that did not exist, then the entire limit wouldn't exist. But yeah, we're able to just kind of say, we can rely on our calculus 1 knowledge of limits to evaluate these vector valued functions because we can just do it component wise. So not too bad there. Here's the definition of space curve. It's something that we've already pretty much looked at. So yeah, we don't need to spend much time on that. I had it up at the beginning. Example number 3, the intersection of a cylinder and this plane is shown in figure 2. Describe this curve in terms of a vector function r of t. And actually, I remember that these pictures are here. Yeah. So the idea is we're going to try to come up with some r of t. A vector valued function that, yeah, would fly around this circular, well, elliptical path. And in order to do that, we need to come up with a good parameterization. Notice that in the XY direction, again, we've got this circular cylinder. So that, yeah, if we look down, we would have a perfect circle. And that is a hint that using sine and cosine is a really good way to parameterize that because we're making, yeah, use of the fact that we have a circle. So using polar coordinates as x is cosine of t, y is sine of t, we could then figure out what z would need to be based on this equation. And if we solve for z there, we would get z is equal to 2 minus x. And with this parameterization, we would have 2 minus the cosine of t because x is equal to the cosine of t. So if we put these in there, this will be one parameterization that works out really well. If you didn't see the fact that we have a circle here and you tried making a parameterization another way, you know, maybe one thing that you might do is notice, all right, so I'm going to do this in a different color. You might notice that x appears in both of those. So maybe you decide, all right, let's make x equal to t, and then solve for y and solve for z in the other equation and see what we get. So if we let x equals t, then solving for y, we would subtract x squared from both sides and then take the square root of both sides to get y is equal to the square root of 4 minus t squared. And again, we're going to get into that situation where we're only going to get half of the circle that we want to because we've only got the positive part. I guess, you know, when you take the square root of both sides, you'd probably really want to put a plus or minus in here But that means that you're looking at two different vector valued functions. So I'll write a little plus or minus there, but this is something that gets tricky. If we were going to complete this though, just, for the sake of trying it, this part would be nicer because z would just be 2 minus t. Yeah. So it is possible to come up with alternate parameterizations. It's just some of them are more elegant than others. Let's take a look at these. Okay, so here we have our cylinder and the plane that's intersecting it. Nope. Good grief. All right, C is our curve here, and I put that in as the parameterization with the cosine and the sine. And what was I? Is this the right? Hold the phone. I did not take into account the fact that we had a 4 here. What was I thinking? Okay, if x is equal to yeah, if x is equal to cosine of t and y is equal to sine of t, we want the 2 cosine and t of sine and 2 sine of t. Sorry, guys. You probably see this. We need to incorporate that 4. Everything has a radius of 2. Oh, duh. Okay, because in polar coordinates, sorry, in general, polar coordinates normally looks like x equals r times the cosine of theta, and y normally looks like y equals r times the sine of theta. I just forgot to put the r's in there. Yeah, r is 2 because the radius of that circle is 2. So real quick, I'm sorry about that. 2 times cosine of t and 2 sine t. And then this part is 2 minus 2 cosine t. Sorry, but that's happening because the radius of our circle is 2. So going back to the graph, that's what that space curve looks like. Pretty cool. If I get rid of this one, this is the alternate parameterization that we found earlier with the t and the square root of 4 minus t squared. Notice that we only get half of that ellipse that we wanted. I suppose I could duplicate that and put a minus sign here and get the other half. But you kind of have to use 2 curves to accomplish the same thing that you could do with 1 up here. So yeah, that one's a little bit more elegant. Yeah, so that's cool. And soon, I did make a tangent vector here. We're going to learn how to make a derivative and make a tangent vector that goes around the curve. So that's going to be cool. All right, going back. So yeah, in order to do that, we are using the 2 equations that we're given to make a set of parametric equations that satisfies all of them. And because this is a circle, the cosine and sine thing is a good thing to try first. All right, now we're going to start doing some some more calculus. Differentiation. We have our difference quotient here. And know that, yeah, r of t is still a vector. So expanding this difference on top looks like you're doing a vector subtraction. And you can do this component wise, and you get limits, and then you see that the derivative of a vector valued function is just the individual derivatives of each of the components. And that's why we're starting off this way. This kind of derivation is kind of the most similar to what you've done before, and the partial derivative stuff that we'll talk about later is a little bit weirder. But yeah, pretty straightforward. You just find the derivative of each component independently. So example number 4, we're given our initial vector valued function, and then we take the derivative of the x, take the derivative of y, and take the derivative of the z component, and we get that. In GeoGebra, I've plotted r of t that we were given, and GeoGebra is pretty handy such that if you put this in as a curve initially, you can just use the prime notation. Just, start off with r prime. Can't even see what I'm typing. R prime, and you'd want to put of t just so that it knows that. But once you do that, you come up with a new curve, and that's actually the derivative curve. Know that this derivative curve is like, it's where if a vector was stationed at the origin, it's where the tip of the vector would go as the t values range from -10 to 10. But instead of looking at the derivative curve, I tend to like to look at derivatives in this context as a vector that starts at the point where you're trying to find the, the derivative. So here's where, okay, now I'm using a as my t parameter. But yeah, this little a is our slider. And this is, t is equal to 0.1, and t goes all the way up to 3. Yeah. But I kind of like to put this vector with its origin at the point where we're evaluating the derivative, so that we can see, I don't know, that this vector just zooms along the path, and the magnitude of that vector gives you an indication of how fast the point is moving with respect to t. Like a change in t induces a change in how fast the point's moving. So I like to look at things like that. But know that instead of looking at that vector, another way to consider this is to not look at what I had before, but know that this vector, when it starts at the origin, traces around all the points on the derivative function. So that this vector is the same thing as the red one. It's just that the red one was flying along the original curve. That's just how I tend to visualize things. Cool. All right, so we've looked at limits. Now we've looked at derivatives. Again, you just do them component-wise. Now we get into a little bit harder of a problem, but not too much. Find the vector form of an equation for a line tangent to this helix traced out by cosine, sine, and t at this point where basically t is equal to pi over 4. I know that these are 1 over the square root of 2's, but that's just what happens when you put in pi over 4 into cosine and sine. And again, the idea here will be if we want to find a tangent line, we have a point that the line's going to go through. And the other thing that we need to make a line in 3D space is a direction vector. And the direction vector is given to us by the derivative. So real quick, let's find the derivative r prime of t. We go component wise. We take the derivative of cosine with respect to t, and we get negative sine. We take the derivative of sine and get cosine, and we take the derivative of t and get 1. And now we have a good direction vector. So if we wanted to find the actual direction vector at the point that we're given, we would do r prime evaluated at t equals pi halves, or pi fourths, sorry. And if we've got negative sine of pi fourths, then that would be negative 1 over the square root of 2. Cosine of pi fourths would be 1 over the square root of 2. And 1 is just going to be 1. So this one is our direction vector. And this one's our starting point. And to put all of that together, we could make, I don't know, line of t equal to, and I'm actually gonna, sorry, flip-flop notation, but I like, well, no, I don't have to flip-flop. I can just do this. We'd multiply this entire vector. I like writing it like traffic lights. This whole vector times t, and then plus the starting point. And that's a perfectly good equation for a tangent line in 3-dimensional space. We can go ahead and look at this. And there we have it. Our helix is there in black. A is our point. That's the starting point. And yeah, all I did was evaluate the derivative at pi fourths to get our direction vector. And that's, yeah, exactly what we had before. So that gives us the direction of the line. And there we have a tangent line. Pretty cool. All right, so that's example 5. Their differentiation rules, all the basic stuff from Calc 1, same thing, except we're doing it component wise now. I guess these two are new, dot product rule and cross product rule. But notice that they have similar overall forms to the old school product rule. In the fact that we have, well, yeah, I guess what you'd be familiar with back in Calc 1 would be something like f prime times g plus f times g prime for 2 functions f and g that you were multiplying together. But yeah, that pattern works out both for the dot product and for the cross product when you take the dot product or cross product of vector valued functions. I didn't need to erase that. And yeah, if you want to work through what that looks like using the limit definition of derivative, this is that. It's something that you would, never have to do again in this class. So it's just kind of there for looking cool, but yeah, you're able to basically say, do the cross product using that limit definition of the derivative, and then combine things strategically again so that you're finding that you have a derivative for this difference quotient and you have a derivative for this difference quotient, and then those ones are just what they are. So yeah, that kind of thing can be used to prove where these rules come from, but basically we're just going to be trying to apply these things. One of the cool consequences of, in this case, the dot product rule, is that whenever you have a vector function of constant magnitude, so that means it's of a constant distance away from the origin the entire time. So you can think about a space curve being traced out on like the surface of a sphere, that the vector that goes to the point on the sphere from the origin is always going to be orthogonal to the vector that's on the outside of the sphere that's tangent to the sphere. And using the dot product rule is one way to show that that happens. And we'll look at it on the graph soon, but basically there's two ways to look at this. One is that when you take the dot product of a vector with itself, you get the magnitude squared. So one way of interpreting this is, as t changes, how does the magnitude of our vector valued function change? Well, it doesn't change at all. We've said that this is a vector function of constant magnitude. So in that way of looking at it, we're zero in terms of a derivative. On the other hand, if you use the dot product rule, you multiply it out and you get some primes, and you get 2 times r prime dotted with r and itself, and then equating those two ways of looking at the derivative of r of t dotted with r of t shows you that when you divide both sides by 2, r prime of t dotted with r of t is equal to 0, meaning that the tangent vector is perpendicular to the position vector. And it took me a long while to figure out, how do I make a vector valued function of constant magnitude. Eventually I figured it out. Essentially, this is the vector valued function that I came up with. I just put like t squared, and 1 in for the components. But then I thought, oh, in order to keep it a magnitude of 1, say, I just need to divide by the magnitude of what this top vector would be. So if I divide by, square root of t squared plus t to the 4th plus 1, all of these squared and added together, that actually makes a unit vector all the time. And what that problem was saying is that the position vector used to generate the curve, so the blue one that's kind of dotted right now because it's inside the sphere, that's always going to be perpendicular to the tangent vector, no matter where we are. And for this particular function, the point moves pretty slowly for certain values of t, and then speeds up and then slows down again. But yeah, I just made this function up out of thin air. It's not necessarily in our book. but it does fit on the surface of the sphere. So that's cool. All right. So yeah, dot product rule coming into play. Cool to see a position vector always orthogonal to a tangent vector. Okay. The last major order of business is to look at integration of vector functions. And the same pattern that has been creeping up is going to continue here. All we're going to do is do component-wise integration. So when we have our vector valued function, taking the integral of that vector valued function is going to look like taking the integral of each of the components separately. And this is just alternate notation where we've got I hat, j hat, and k hat instead of bounding everything in vector notation like that. Both of those are fine. But yeah, the fundamental theorem of calculus still works. This definite integral is the difference between the antiderivative evaluated at the endpoint minus the antiderivative evaluated at the starting point A. So that all still works. And yeah, all of these bold letters are just, they're all vectors. Let's take a look at what that might be in a specific case. Here we have a ball shot by a slingshot into the air with an initial velocity vector of 0, 10, and 64. So that means it is going nowhere in terms of the x direction. It is going 10 units in the positive y direction and 64 units in the positive z direction. So we've got kind of a, an angly thing, but it's going up. This is measured in feet per second. What we want to do is determine the velocity and position functions, in terms of t. And then we'll find the position of the ball at 2 seconds and 4 seconds. So in order to be able to use integration to find these things, we're going to need to go back to first principles. And I mean, if you think about integration, we're going to be working backwards from differentiation. So if we want to get velocity through integration, we need to start at acceleration and then work backwards to velocity, then work backwards to position. So the first thing, we're shooting a ball with a slingshot. Physically, what's accelerating that ball? Well, the only thing is gravity is working on that ball. So I'm going to make a function, call it a of t. Again, this is a vector valued function, but this is for the acceleration due to gravity. Gravity won't affect it at all in the x or y direction, but gravity will be a negative 32 feet per second in the z direction. So that's an important first piece. Taking the antiderivative of all of those component-wise, we can come up with v of t, the velocity, the antiderivative of 0, 0 still, or I guess possibly you could have a plus c there. Am I crazy? When you take the antiderivative of a constant, oh, you get a t. No, you don't get a t. You would get a constant. Maybe a non-zero value. Oh my goodness. I haven't done this in a while. This is a dumb place to be. Maybe we could have. Oh, it's okay. These are constants that could possibly be there, but they're going to depend on the initial condition. So, okay, that's what it is. Okay, sorry. I'm going to write 0, 0, and then negative 32t here. But know that we have another vector c here that would be some possible constant vector, and that's going to depend on what happens when you put in 0 for t. And so this constant vector is actually given to us by the initial vector um, 0, 10, and 64. So that's the way that we turn kind of this general antiderivative where really we have a family of vector valued functions here. The initial condition on the velocity allows us to pinpoint what this extra constant vector will be. And we could totally add those together to get something that looks nice overall. We just have 10 for y, and then negative 32t plus 64 for the z component. Okay, sorry. We're figuring this out. We got it. One more time, taking an antiderivative. I guess, yeah, I should have written over here antiderivative of a of t gives us v of t. Antiderivative of v of t gives us r of t. And this will be our position function. But yeah, again, we're going to take a look at what we have. So we'll have 0, 10t, and negative 32, nope, sorry, negative 16t squared plus 64t. And then we would have some vector of constants that, technically we have a family of functions right now, but the initial position, this is the initial position. So I guess I could, write that again. For sake of graphing, I'm going to make the initial position just equal to the origin. So this part will just not even be worrisome. Okay. And honestly, if you were using the velocity function to as the derivative of the position function and using the fundamental theorem of calculus to derive this, one of the ways that you could do it is set up, in order to find the position of the ball at say 2 seconds, which would be r of 2. I mean, it'd be easy just to plug 2 in here and get it that way. But using the fundamental theorem of calculus, you could take the integral from 0 to 2 of v of t to get your answer that way. And that would give you the same vector. And, for v of t, you don't even have to worry about this plus c being a part of it, because when you do this antiderivative minus another antiderivative, these plus c's would, the plus c's cancel out. Anyways, the simplest way to do this will just be to plug 2 into this equation and 4 into this equation, and we would have our answers completely. I think when you put in 2, you get a vector that's 20 and then 0. No. I think you get it 64. Anyways, let's look at the graph and that'll make sure that we know where we're going. And actually, what we did solving for these antiderivatives in a general sense gives us plenty of options, more than just to find the position of the ball at 2 seconds and 4 seconds. We can find it whenever we want, because all we have to do is put in a different t value. But anyway, here we go. We've got the position curve in black. So that's the arc that the slingshot ball would follow. I have a tangent vector in red, and I actually put the acceleration vector here in green. And this is what it would look like for different values of t. And again, I'm using w as the slider. So yeah, our slingshot gets launched into the air, hangs out for a while, falls back down. And in order to get, the exact vectors we want, we would just put in 2 for our parameter. That's when we hit the apex of our path. Yeah, and the vector there would be 0, 20, and 64 would be the height. Okay. And then 4 at the end, we would be at 40 and 0 for the z value in terms of our position. But yeah, making something like this and going through the effort allows you to just get whatever t value you want, and you're able to see all of those things working together. So yeah, I don't know. I think that's cool. All right. And that's it. We've looked at limits, we've looked at derivatives, we've looked at integration real quick. And that's the kind of things that will show up on your homework. In this section, you'll have one problem where you parameterize a space curve at the intersection of two things. You guys can totally do that. Hint, you've got a cylinder on one of them where it's a circular cylinder. Here is, yeah, one where you're finding the tangent vector, or actually you're finding the whole line tangent to that curve, where finding the tangent vector is part of that. And the last one is about integration, I think. Yeah, so you're doing acceleration and velocity and position again. And if you have time to work on those, great. Otherwise, I will see you in our next class. We will look at section 12.2, and we'll keep playing with this stuff. All right, thank you guys. Thank you for working hard. We'll see you tomorrow.